Greetings everyone. Now that we're in the two-dimensional rectangular coordinate system, it's time to move up our linear equations as well into two variables. Instead of just solving, now we're actually going to be analyzing the equations and the graphs that are associated with them. And as you can guess from the name, we finally get to make that connection. We will be graphing lines for linear equations, right? So let's start by talking about the first form that's usually associated, when creating these equations from word problems and things like that, and that's general form. General form is a version of a linear equation where x and y don't have any significant importance or relationship more above each other. They sort of have equal ground. They're both on the same side of the equation. As I said before, it's typically easy to make an equation like this from word problems if you have two different situations going on and you're just bringing them together to make an equation. It's not one of the forms that we typically give lines in later on because of the way we deal with functions and things like that, but it is definitely the most widely known because you have your variables all on one side and everything is to the one power, and you sort of just have that everything going on one side thing, right? So, okay, so from general form, the A, the B, and the C, they don't technically by themselves have any particular meaning as far as the generic equation itself. Of course, the A and the B and the C could have meaning if you were actually applying this to some sort of word problem. A would be, the contribution for the x, and B could be the contribution of the y and things like that, and C could be a total. But I mean, in general, pun intended, when we're talking about just these equations and the lines, they by themselves don't have any important meaning there. Okay? So the first thing that immediately comes to mind is we would probably want to also be able to graph from these, okay? And the quickest way from general form is to just create both of the intercepts that the line is going to have, okay? Except for a few very special cases, all of your lines are going to have the two intercepts. If it has both of the x and y variables in your equation, then it's going to have an intercept for each. The only special case where you wouldn't be able to just use those two is in case x and y intercepts are both the origin. But most of the time that's not going to happen. Okay, so here we go. When you're going to make these intercepts, don't forget the y-intercept is defined as when x is equal to 0, right? That's not just a y-intercept, that's any point on the y-axis. But we're going to apply this definition to x and y-intercept because we have a certain equation and we're going to let x be 0. If I do let x be 0, notice that I'm just left with b times y equals c, right? If x is 0, this is all I have. And so if I solve for y, I actually get c divided by b. Same thing for the other intercept. The x-intercept is when y is 0. So if I plug in 0 for y, then I've got ax equals c. So c divided by a would be my x value in that case. Okay, so these aren't really, big generic formulas or anything you should memorize. It's just a way to organize our thoughts here, okay? Because you can actually just remember the definitions of these and plug them in and solve at any given point. In fact, that's true for any equation that we're going to run into that we would want to be graphing. Intercepts become some very quick and easy and efficient points that we always want to use in graphs, okay? So then, let's take an example right here of this line. Again, I know it's a line because it's linear, right? X to the 1, y to the 1. Remember our definition of linear, everything's to the 1 power. And I know it's a line because it's the two variable kind of linear, right? The one variable kind of linear we did was just solving and we get a solution. If you do more than two variables, they're not lines anymore either. You can get planes and hypercubes and things like that. Okay, so we're not worrying about that. If you've got your two variables and they're linear variables, then you're graphing a line. Okay? So then I'm going to calculate my x and y intercepts by plugging in 0 for each one. So my x-intercept is when y is 0, right? So if y is 0, it's just gone. I do this cover-up method. 5x equals 12. Well, that just means I'd have to divide by 5 on both sides, and so I'll get 12 fifths. Okay? 12 fifths, though, is kind of hard to find on the grid. So I actually do 12 divided by 5. 10 divided by 5 is 2, and then 2 fifths is 0.4. So we've got 2.4 here for that value. All right, y-intercept. I let x be 0, and I'm left with negative 6y equals 12. If I divide both sides by negative 6, 12 divided by negative 6 gives me negative 2. Okay, so from there, I would just want to plot those 2 points, and that's really the minimum that you can get away with. If I can plot 2 separate points, that's always going to create one unique line. Okay, so let's do that. I have 2.4 x-intercept. That's going to be somewhere right about right here. And then negative 2 y-intercept is exactly right here. Okay. Let's see. Line this up. And there we have it. The graph of the line, right? Okay. So from standard form, a lot of times you were just going to graph by using the intercepts. The only off chance that you would need to do something else is, like I said, if both of the intercepts end up being 0, 0, right, your x and y intercept are the same thing, then you may have to plug in another point, and that's acceptable to do too, right? Or plug in another point, right? And if you have to do that, all you really do is just pick a random number, an x or a y, it doesn't matter which, you would just plug it in. Like, for example, what happens if I plug in 5 for y or something like that, right? Or let's pick something a little bit closer down to easy to graph. What if I pick 1 for y, right? When y equals 1. So then you just plug in your value. 5x minus 6 times 1 equals 12. And then you just got a linear equation to solve, right? This is just 6, so I would add 6 to both sides. 5x would then be equal to 18. Divide both sides by 18. Divide both sides by 5. Right? 18 divided by 5 is going to be 3 3 fifths, so 3.6. Right? So when y is 1, x is 3.6, and you'll notice that the point that we're getting is right here, which is the same line that we drew before. So it's okay to plug in other points, but typically we only do that when we have no other choice. It's really easy to plug in 0 and get these intercepts, and you can really grind them out quick, and then they're usually easy to graph because they're already on an axis. It's easy to find them. Okay, like I said before, I would only do this if I didn't have another choice, like if my intercepts were the same number or something like that. Okay, so that's standard form or general form of a line, and that's when x and y sort of don't have any importance over each other, and they're all on one side. But eventually we're going to be studying functions and things like that, and we typically like to have our y variable on one side. Okay, so we're going to switch gears now, and we're going to talk about the slope-intercept form, which I'm sure you've probably seen before. Y equals mx plus b, right? Notice the y being on one side, and then x is sort of doing all the heavy lifting over here inside of the calculation of the line. So before we get to that though, let's go ahead and define slope, just so that we can have it officially down there, right? So slope is basically how steep your line is, okay? Pure definition, it's a measure of the incline on the graph, how steep the line is by incline, right? And it does this measurement by a ratio of how far out it goes. Well, let's do it the correct way. How far up it goes versus how far out it goes. Rise divided by run. It uses that ratio to make a comparison. It may not always feel like it, but things that are in fractions, things that use division like that, another way of thinking about that is that you're actually comparing these two quantities. Okay? If the rise and the run are equal, for example, and you're dividing, you get a slope of 1. Okay? So whenever your slope is 1, you have this steady 45-degree angle where the rise and the run are equal. Okay? So you get the idea that this is more of a comparison, not just a division. Okay? In real life, we also use the same idea for slope as whenever we're measuring some sort of change. For example, whenever you're driving your car, you measure your speed in miles per hour. That's technically miles in a fraction over hours, right? But you don't ever think of it as a fraction, miles over hours. It's miles per hour, like one thing changing while the other one's changing, right? So it measures that change, again, by comparison in a ratio. And that's what slope is. It's measuring by ratio, by comparison in a ratio, okay? So if you have 2 points, the thing that you need to do is actually calculate how far it goes up and how far it goes out, right? And you can do that by subtraction, because how far it goes out, for example, that's just a one-dimensional distance. One-dimensional measurement is always subtraction. Even when you're using like a ruler or a tape measure, you usually just read the number off the tape measure, but technically you could start anywhere in the tape measure. Like if I measured from 1 to 5 on a tape measure, that'd be a distance of 4, because it's 5 minus 1. Okay, same thing here. If you're only moving in one dimension, you simply subtract, and that's a measurement in that dimension. Okay, so right here, if I do that for both of these, each one is a subtraction. Just subtract the two x's, right? The ending minus the beginning. Same thing here for the y's, ending minus the beginning on the y's. And then once you've done that calculation, the definition of slope kicks in. Rise divided by run. So then I have this nice little formula for how to calculate a slope if I have 2 points. Okay? So, now that we've talked a little bit about slope, how does it build into lines? Well, lines really are over-glorified slope. If you're dealing with a linear situation and lines are the models that you're using, more than likely the slope is going to be the thing that you're most interested in. Okay? Because that's what lines are going to be used for. Measuring some sort of slope, some sort of change, some sort of steady increase or decrease of something like that. All right? So slope-intercept form has exactly what we're looking for in it, right? It has that slope. It's the value m, okay? I know, why don't we use s? First of all, s is kind of because it looks like 5. But m is just the traditional, what we've always used for slope. It has some French roots. You should go look it up. Okay, so anyway, m is our slope times x. That should sort of make sense to you, because remember, m is a rate of change. It's measuring some sort of how fast something is changing or how steeply it's inclined, right? So in other words, how much x is contributing, right, to get a y value out. And then the y-intercept here is just sort of an offset, right? I'm adding it in as an afterthought after I multiply m and x, because it's how far should I bring this away from the origin? How much should I offset this? What number should I start at is another way of interpreting this, right? Y-intercept is sort of a beginning value if you're going to read from left to right, okay? In any case, this is the most common format that we have for conveying lines, writing lines, communicating lines. It's in our functional form where y is isolated, okay? However, it's not always the easiest to create just right off the fly, right? So we have a couple of other equations that are built out of this slope formula here, okay? And I've got two other versions of it. The point slope form is literally I'm taking this subtraction of x's and just multiplying it to the other side. You'll notice that's exactly what this is. The x minus x used to be in the denominator here. It just got multiplied over. And that's point slope form there, okay? But it's used in a reverse. Here, when you're calculating a slope, you're actually, plugging in some numbers here when you're doing that, and you're getting a slope out. When you're building an equation here with one of these, that's what these are used for, used for building linear equations. You're actually plugging the slope in like you already have it. And then you're also plugging in one point. That's what the x0 and the y0, we pronounce that x naught and y naught. Okay? That's what those are. I'm plugging in some other point that I happen to know on the line. And then usually that gives me something that I can simplify. Okay? Now I have this other version of point slope that you don't actually see very often. And what this is a way for us to avoid fractional difficulties. Okay? If you're looking for something quick and you don't really want to deal with fractions, sometimes your slope is in a fraction form. Okay? This is another way of writing your slope so that you can plug in all of the pieces, simplify it down another way, and still get the same result, and for the most part avoiding fractions. Okay? Notice the only difference, I've still got the y minus y and the x minus x in the same spots. And then delta y is where the slope used to be, and delta x is now multiplied over here. And don't forget, slope is really just that rise over run, right? Rise is delta y, run is delta x. All I did was I multiplied delta x to the other side here. Okay? So this is something that you'll see when we're creating lines. If I know that my slope is going to be some sort of fraction, sometimes we'll set it up this other way just to help speed things up. And that's really all it is. Okay? You usually only see this displayed as point slope, but I've got that other version to sort of, I got your back, Jack, right? Okay. So, okay, first example though is how would I graph from slope-intercept form? Okay, let's start with the graphing end, and then we'll come back in with the examples of how to create with using those two right there after we talk a little bit more about slope. First of all, an example with slope though is to take this same line that we just graphed a moment ago, 5x minus 6y equals 12, but let's convert it into slope-intercept form, and let's talk about how I could also graph using the idea of slope and an intercept. Okay? So first of all, let's convert it. To get into slope-intercept form, the goal is to have y by itself on one side. So the first thing I do is I subtract the 5x over. You'll notice I subtract the 5x from both sides to get it out of the way here, and it becomes a negative 5x on the right-hand side. Still plus 12 is still there, and the negative 6y is still there. If I want y by itself, I'm going to have to divide. So if I divide by negative 6 in all three places, right? Divide by negative 6 here, you'll get y. Divide by negative 6 here, and you'll get 5 over 6 because it'll be a double negative. And then 12 divided by negative 6 is negative 2. Well, that should look familiar. Look, y-intercept is negative 2. We already calculated that, right? That was already there. Okay, but now it's in this equation. You should be able to read it out of the equation. Oh, look, that's my y-intercept. Whenever you see a linear equation in slope-intercept form, that's where that number goes, right? Oh, look, slope-intercept form. It's got to be the y-intercept is that last number. Then my slope right here, right, is 5/6. So that means if I pick any point on the line, okay, and if I count 5/6 slope, that would be a rise and a run, I should land on the line again, on another point on the same line, okay? So that's how I can actually use this to help me graph this line. if I were going to graph this line, right, just pretend it's not on here for a moment, I would start with the y-intercept. In other words, I would graph this point first here, right? This point, the -2 for the y-intercept. Now 5/6 is the slope, right? What that means is that I have a rise of 5 and a run of 6. Now I also want you to realize that I could go in two different directions, because I could also go a rise of -5 as long as I remember to run -6. And we typically don't do that. We typically like our run to be positive because that's how we read from left to right. But keep in mind that I can actually do that because negative divided by negative is still positive. Okay? So if I'm going to graph that from here, I start with my y-intercept, -2, and I'm going to count, I'll use the top one, a rise of 5. That would be 1, 2, 3, 4, 5. From here, I would then count a run of 6. 1, 2, 3, 4, 5, 6. So notice that would land me right here. Okay? So I went up 5 and right 6. And that's the slope of this line. You could have done that from any point on this line, and you would land again back on that line after you counted a rise of 5 and a run of 6. And again, I could do it the other way. I could do a rise of -5 as long as I did a run of -6. And notice I would still get on that same line. Okay? So keep in mind that slope is a way of counting while staying on a line, right? It's a roadmap from one point to another point on the same line, if you will, right? So I have a starting point and I've got a map to another point for any line, actually. So sometimes this can be more efficient of a way of graphing, especially if it's already in slope-intercept and you don't have to convert. That's a very efficient way to graph one of these lines. Really quick, let's take a look at that same line that we graphed two different ways. It's 5x minus 6y equals 12. Let's zoom in a little here. And notice the intercepts here. -2 as we calculated, and 2.4 as we calculated. And then also notice the slope, right? If I were to count up 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, 6, run, and I get my other point that we graphed. To continue where we were in the mix there, we need to talk about the different types of slope that we'll be encountering. And really there's just 4 main types and then a couple of little relationships that go between some slopes. So let's talk about all of that. First, we have the increasing type, and it's named increasing because remember, we like to read left to right, and notice it rises as we read from left to right. So it's gaining y value, it's increasing. Okay? If I calculate the slope for this, the way we were talking about before, this is just an example, but it's an example of something that's rising to the right. So let me calculate the slope here. M equals y2 minus y1 over x2 minus x1. So here I've got 4 divided by 9. Okay? So I want you to notice that the overall slope is positive. whenever we're just looking at the different equations and calculating things and we don't really have a graph in front of us or whatever else, one thing you need to be able to tell right away, oh, my slope's positive, my line must be increasing. That's the connection there, okay? Now, of course, when you're actually graphing the line, like we did earlier, you can interpret the slope two different ways. You can interpret as a 4 up and a 9 right, but you can also interpret it as negative and negative, so you could go down 4 and left 9. That actually ends up being the same thing, because it just depends on where you start and where you finish, right? I could go up 4 and right 9 that way, or from this point, I could go down 4 and left 9. It's the same thing. Overall, the slope is positive, okay? Next, of course, if we do increasing, we're going to have decreasing, right? That's just the pair of the way it goes. So again, notice as I'm reading from left to right, it is losing y value. It's dropping from left to the right. Okay, so let's compute the slope here. y2, 6, minus y1, negative 2, over x2 minus x1. So what I'm getting here is 8 over negative 7. So overall, I'm getting a negative 7/8. I'm sorry, negative 8/7. Whew, I don't know why I said that. So again, notice it's a negative slope, as you would expect. Okay, because of course increasing was a positive slope, decreasing should be the opposite. It's a negative slope. Okay, and I also want you to think bigger picture here. Remember, we said slope by definition was a measurement of change. So it makes sense that a positive slope would be an increase, because positive is like adding. I'm gaining, I'm increasing, right? It's changing in the positive direction. Opposite the other way. If I'm decreasing, I'm losing, it's falling. I'm going to have a subtraction. It's a negative slope, a negative change in something, okay? These two types are your main types. That covers, 99% of all the lines that we run into. And these two slopes are what you expect when you're dealing with the general form equation or the slope-intercept form of the equation. These are the types of lines that you're always going to be dealing with all of those different equation forms that we just talked about, okay? Now, of course, there's two other types of slope to talk about, but they're special cases, and they're such special cases that I don't even need to have all of the other grand equations and things like that. They're very, very refined and specialized, okay? So here's these next two here, the horizontal lines and the vertical lines, okay? The horizontal lines are going to occur whenever they all have the same y value, okay? That alone tells you exactly what the equation of this line is. Notice both of the points here have the same y value, right? Okay, so you can describe all of the points on that line that way. And in fact, that's where the equation for this kind of line comes from. The equation of this line right here is y equals negative 2. Notice I don't need my y equals mx plus b or ax plus by equals c or anything like that. I can describe that equation by saying every point that has a y coordinate of negative 2. Boom, that's the explanation of that line. And that's what it is. It's a collection of all of those such points. So I can just say y is negative 2. And that's my collection. Okay? Also, though, I can compute a slope here. Right? Let's do that. Let's compute the slope on a horizontal line here. M equals y2 minus y1, so negative 2 minus negative 2 over 5 minus negative 2. I want you to notice the top is 0 and the bottom is just some number, any number, depending on the points I picked, right? Which comes out to be 0. for any horizontal line, the slope is going to be 0. Okay? Zero slope. So whenever you run into a situation that's dealing with this kind of line, these three pieces of information go together, like immediately. They should in your head. You should practice this until these three are synonymous. These three pieces of information: horizontal line, 0 slope, and y equals some number. Okay? Those three pieces of information just go together for any situation. And there's not really any calculation necessary. You just know, oh, it's horizontal. Oh, well, then the slope must be 0. Okay? Vice versa. Talk about vertical. Same kind of idea. But instead of y's, notice all of the x's are going to be the same here. Right? Well, this has an x coordinate of 3. This has an x coordinate of 3. This is just one example. Vertical line could have been anywhere. Right? Every other point on this vertical line is also going to have an x coordinate of 3. So the equation here is x equals 3. And I know these sound like solutions to when we were solving things before, but remember, we're in a 2D system. If I only give you one variable in a 2-variable system, then that means the other variable can be whatever it wants. I'm just telling you x is 3 right now, and that's what you get. Okay, let's also do a slope calculation. So I have m equals y2 minus y1 over x2 minus x1. 4 minus negative 4 is 8, and 3 minus 3 is 0. Okay, this is important. Notice the 0 still happened, but this time it's in the run. It has 0 run, no run. Right? This is undefined. Remember, we can't divide by 0. That's a big, big no-no. So it's an undefined slope. Not to be confused with 0 slope. Right? That's horizontal. Undefined slope is vertical. And that's important. Don't get those mixed up. Undefined means there's not a number that I can use to describe this slope. Period. Okay? Vertical lines, they don't have any run, so there's no change to measure. That's one way of thinking of it. Or there's too much change with no time passing to measure. That's another way to think of it. There's so many ways that you can go about this, but in any case, no matter which way you think of it, there's not a number that you can prescribe to the situation. Okay, so again, three pieces of information that just go together, and you just need to know it. You need to know it in your head and just be able to crank them out. If it's vertical, the equation is x equals some number, and the slope is undefined, right? Vertical, x equals a number, slope undefined. That's three pieces of information. Horizontal, y equals a number, slope is 0. That's three pieces of information. They just go together. Okay, special cases on those. And then to finish up our conversation about slope, there's two important relationships that come up all the time, right? Parallel and perpendicular. Let's talk about parallel for a moment, okay? Of course, by definition, parallel means two lines that don't intersect, right? That's what everybody always says. Be careful, because if you ever increase the amount of variables and things like that later on in your math career, you're going to have to get more specific, because I can have two lines that don't intersect that are not parallel. For example, if I do my markers like this, right? If you look at them like this, it looks like they intersect, right? But notice they actually don't, right? So if I have a third dimension, which we don't here, I know, then they don't intersect. Those are called skew. Definition of parallel is two lines that are in the same plane that don't intersect. And that's what we have, right? We're considering this board to be our plane. And these two lines are in that same plane, okay? And they don't intersect. The symbol for parallel is either two straight up and down lines, although that kind of looks like absolute value or 11. So I kind of slant mine, okay? That's the symbol for parallel. And it's really easy to see if you look at the same x values on these two different lines and actually calculate the slope on each one, you'll notice that the only way that these two lines can stay this exact same distance apart, that's how they're parallel, that distance between them never changes, right? The only way that can happen is if they're running and rising at the same rate. And there's that word rate again, right? In other words, they're changing by the same amount. It's kind of like that guy on the interstate that you're going the same speed as, right? You never pass him up, he never passes you up. Y'all just kind of stay parallel the whole time because your rates of change are equal. And that's what's happening here. The rises and the runs are the same to keep those lines the same distance all the time. So the slopes have to be equal, okay? Again, that's just things that just come with the words. If you see parallel lines, slopes have to be equal, okay? Now, on the other hand, perpendicular. By definition, perpendicular are any two lines that meet to form a 90-degree angle, a right angle, okay? Now, that may sound sort of just trivial, like, oh, okay, here's a right angle. It's important here. The right angle relates back to our entire system. Our x and y axis are perpendicular. They make a right angle. All of the different intersections of all of the different x and y lines make right angles. We are in a right angle system. So you come up with a special situation that creates right angles, it's going to have this nice, pretty fit into our system. And this is what it is. Notice whenever you create a slope, right? Whenever we do a rise and a run, just sort of graphically draw it out or picture it in our mind, we always have that right angle. And that right angle is always oriented the same as the x and y axis, right? Because this is a y line and this is technically an x line right here. So they're going to be at a right angle because our x and y axis are defined that way, okay? Same thing for this slope over here. I have a y line and an x line. Now, what would happen if I were to rotate this thing, right? In other words, grab it like a steering wheel and just rotate it. Okay, well, since this is 90 degrees, if I rotate it 90 degrees, this triangle would rotate into this position exactly. If I rotate it 90 degrees, the lines would basically switch positions. Okay, so if I'm drawing out this slope and then I rotate it 90 degrees, it basically becomes this other slope, right? And it's okay, they're both lined up appropriately. These two right angles here are now lined up with the system correctly. So because these two are at a right angle with each other, their slopes line up perfectly no matter which way you orient the wheel, if you will, right? Well, that's a symmetry. They have some sort of equality going for them there, right? Well, here's what happens. When you do that actual rotation, notice the A here is a rise, whereas the A here is a run. And then vice versa. B is a run, over here B is a rise. And we have this line that's increasing, right? Should be a positive slope. Whereas this line right here is decreasing, should be a negative slope. So altogether, here you can notice the slope of M here should be negative A over B, negative rise over run. Whereas the slope here is just B over A, rise over run again. Okay? So here's the cold hard fact of it. If you have two lines that are perpendicular, their slopes will be opposite in sign, one positive, one negative, and they will be reciprocals of each other. One will be B over A, the other will be negative A over B. Okay? So perpendicular lines have opposite reciprocal slopes. What this is just a way for us to be able to look at some lines and be like, oh, I know his slope. Well, that means you know the other guy's slope too, right? I can just transfer information from one line to another easily. Okay? The last thing we need to talk about for this section is how to go the other direction. Instead of going from an equation to graphing it or interpreting the equation, now we're going to start with some information and then how do we create the equation of the line from that information, okay? And I've got 4 different main types to show you here, and then pretty much every other situation can be generalized from these 4 situations, all right? Now, of course, the first one here is very straightforward. How would I create the equation of some line when I already know the slope and I already know the intercept, okay? And it goes pretty straight by definition on this one. We have an equation for lines called slope-intercept, right? So when I look at this line here, I'm noticing that I already know the y-intercept, 0, 3. Okay, well, remember in y equals mx plus b, b is that y-intercept. So I already know that my b is the value 3. Also, m, the number in front of x, is our slope in this format, and I already know enough information. I could read 2 of the points. So either I count the run and the rise, or I physically, do the subtractions with the 2 coordinates of the 2 points. Either way, you immediately get the slope out of that as -4/3. Okay, because it's going to run 3 to the right and 4 down. So the slope is rise over run, -4/3. I can immediately set up this equation. Y equals -4/3 x plus 3. So just as easy as it is to graph from slope-intercept by putting a y-intercept and counting the slope, it's the reverse in process. If I can see the intercept and the slope, you can just crank out the equation immediately into slope-intercept form. And that's typically the form of the equation that we like to use anyway, right? Now, of course, from this point, if you need to convert it to standard, you could always just add the x over to this side and then multiply to get rid of any fractions. If I multiply everything by 3 and then add the 4x over, 4x plus 3y equals 9, right? So just, whichever form the problem calls for in that case. Typically, slope-intercept. Next level up, what if you're either given a slope and a point that's not the intercept, or just in general, 2 points, okay? 2 points is enough to graph a line from. 2 points is also enough to create a line equation from. So right here, I'm sort of skipping a rudimentary step up to the next level. You could have just been given the slope and just some point, and we'd be following almost the same process. I'm kind of taking it to the next level. What if all you're given is the 2 points? Well, I can still calculate the slope. If someone hands you 2 points, they're practically handing you a slope. You're just one calculation away, right? So let's do that. Slope calculation here. y2 is 4 minus y1 is -1 divided by x2 minus x1. So I'm getting 5 over 14 as my slope. Okay, so at this point, you either have been given the slope or 2 points and you got the slope. Somehow you've gotten the slope. And the only other information you have is just some point, which we actually have our choice in either one of those. I'll go ahead and pick the 8, 4, just because. Doesn't really matter. I have a slope and I have at least a point. That's all you need to use the other equation that I showed you to create a line equation, and that is point slope. Remember, we had 2 different forms of this one, right? Either y minus y naught equals m x minus x naught, or delta x times y minus y naught equals delta y times x minus x naught. Either one of these versions of point slope will give you the same result, okay? So watch, I'll set them both up and you'll see. Let's set up the first one. Okay, the point that I'm picking is the 8, 4 point here. And then of course my slope is 5 over 14. So if I set up this first guy here, I've got y minus 4, right, because that's my y value, equals my slope, 5 over 14, times x minus 8. So I hope you're noticing right away the immediate need of being able to work with fractions. So either you end up multiplying by a common denominator, which is actually just going to land you in the other setup, or you directly deal with the fractions as they come. So let's do that for a second. Y minus 4 equals, I'm going to distribute. I'll have 5/14 x. And then this will be 14 and 8 will reduce by 2. So I'll have 20 over 7 after you reduce that, right? Because it'll be 40 over 14. And then, so 20 over 7. I still have to get y by itself here by adding 4 to both sides. But instead of putting plus 4 here, I know it's tempting to go ahead and put the 4 there. I'm going to put something there that has the same value as 4, but with a common denominator here. So that would be 28 sevenths. That is a value of 4. 28 divided by 7 is 4. So I'm still adding 4 to both sides. However, I now also have a common denominator. 28 minus 20, I end up with y equals 5 over 14x plus 8 sevenths. Okay? Or if I use the other version of point slope here, then I just need to, in my mind, be able to distinguish what's delta x and what's delta y. If you've already got your slope, you have those. Remember, slope is rise over run. Delta y over delta x. Rise over run. All right. So that means that I can set up this equation. 14 times y minus, I'm still using this for my point, 4, equals delta y is 5 times x minus, x coordinate is 8. All right, so from here, I can solve the same way. I can distribute the 14. So I have 14y minus 56 is equal to 5x minus 40. Okay, I'll add 56 to both sides. So I have 14y is equal to 5x plus 16. And then if I divide both sides by 14, right? Here, 14, 14, 14. Notice I end up in the exact same equation, 5 over 14x, and then this reduces to 8 over 7. Okay? So this is just another way of doing the same thing. Side note, if you had to write it in general form, this is also an easier way to go about doing that, because notice I've already got number times y, number times x. Instead of dividing by 14 here, I could have just subtracted the 5x from both sides, and it would have already been in standard form. So in a lot of different ways, even though this isn't the standard way that you'll see it written in any textbooks, this ends up being an easier way to deal with point slope equation right here. You just have to be able to distinguish your delta y and delta x from your slope once it's given to you, or once you calculate it. Whatever. Okay, so now a couple of situations that are more off to the side using those relationships. One of them with parallel and one of them with perpendicular. And the idea here is you're reading information from some other line and then using that to get information for the line you're currently interested in. So I just need to read the information from this line and then create information for my line for it, right? So first thing I read is, remember, we're interested in getting our slope first, because remember, slope is the most important part of a line. So if I'm going to get my slope first, I'm going to look at which relationship I have. It says parallel, right? Now think back. Parallel meant equal slopes. Oh, okay. So that means I should just be able to take his slope and copy it, right? Here's a little trick for you. When you're in general form, let me write this out on the side right here. when you're in general form, remember we talked about ax plus by equals c. The slope is always negative b over a. Oh, I'm sorry, negative a over b. I got my x's and y's backwards. Sorry. The slope is always negative a over b. It's always whatever number's in front of x divided by the number in front of y, and the opposite of what you see it in this format. Because all you're doing is subtracting and dividing. Okay? So a lot of people will say, oh no, you got to convert that to slope-intercept form, and then you can read the slope off of it. And if you're comfortable with that, fine. Go ahead and convert it into y equals mx plus b, and then you can read it. Or you can remember, hey, Professor Simon said I could just divide these two numbers. And that's what you're going to do when you solve. You're going to divide the numbers and change the sign. So that's all I'm going to do here. The first thing I'm going to note is that this guy's slope right here, right? His slope is negative 5 over 2. So then my slope is also negative 5 over 2, right? That's his slope. My slope. M equals negative 5 over 2. Because I'm copying it, it's parallel. Okay? But I also have a point that it goes through that I want my line to go through. So I have a slope and a point. Well, we're back to this situation again. You have some slope, you have some point. I'm going to set up point slope, right? I'm going to typically do it this other way, the alternate way, especially when we have fractions like this. Okay? So then the question rises, should the negative go with the rise or the run? And the answer is either. But typically, whenever we're interpreting slope, negatives tend to go with the rise because we always like our runs to be positive if we can help it. So that's the way we read. So whenever I'm splitting this up here, negative 5 is going to be my delta y, and 2 is going to be my delta x. There's delta y, there's delta x. Okay? So if I set up my point slope, then I'm going to have 2 times y minus negative 2 is equal to negative 5 times x minus 13. Right? I'm just setting up point slope form again. Right? And there's my delta y, there's my delta x. I'm going to distribute on each one 2y plus 4, because of the double negative, right, is equal to negative 5x plus 65. Okay? So then from here we have a choice. Do we want slope-intercept or do we want standard? Either way, I'm going to subtract the 4 to bring my numbers together. So I have 2y is equal to negative 5x plus 61. Okay? So let's say we wanted to do it in standard form this time, right? If they wanted slope-intercept, I would just divide by 2. Well, I'll go ahead and show you both. Let's do both. If I divide by 2, y equals negative 5 over 2x. Notice the slope is the same, right? And then plus 61 over 2, right? Or if I simply add the 5x over, I'll have 5x plus 2y equals 61. Either one of those is an acceptable answer here because it just said create an equation. So one is the general form, one is the slope-intercept form. Okay? There's a trick also that I can show you with this after I show you this other problem too. We'll talk about there's another little twist here if you're into those sorts of little shortcuts and can remember them and stuff. Okay? Let's concentrate on the main problem first, and then I'll show you the little side dives. Okay, next, create the equation of a line perpendicular this time to some line and goes through some other point. Okay, again, remember, the most important piece of information is the slope. So the first thing I'm noticing is the perpendicular, right? See that first. And then it's applying to this line right here. Okay? What's his slope? His slope is negative a over b. That's negative 7 over negative 9, which is just 7/9. Okay? Now remember, that's the slope of the line that they gave us. That's his slope. Not mine. It says perpendicular this time, right? So my slope is going to be perpendicular, right? Remember, perpendicular is the opposite reciprocal. So he's positive 7/9, so I'm negative 9/7. It's like having one of those arguments, right? Somebody just really makes you mad, and it's like, I'm just going to do everything opposite, right? Just because I know he's wrong, okay? So not only is he positive and I'm negative, but he says 7/9, I say 9/7, right? It's a complete reversal of just about everything a slope is, right? So I'm just reversing it around. Well, we're back at that spot again. I have a slope, I have a point. So I'll be using point slope yet again, right? You'll find that in a lot of situations, even beyond in the next math class that you take. This is where you end up with most of your line type of creation, equation creations. You're going to have some sort of information that gives you a slope, and you need to know a location of your line, right? A slope and a point. It's very, very typical. So again, my delta y is negative 9. My delta x is 7. So I'll set up 7 times y minus 8, right, equals negative 9 times x minus 2, like so. All right, distribute. Negative 9 plus 18. Get all of your numbers together. Plus 56, plus 56. So this is gone. I now have 7y is equal to negative 9x. And then we've got, let's see, 60, 74. Plus 74. So again, where we are, we have a choice. Do we want our answer in slope-intercept, or do I want my answer in general or standard form, right? So if it's slope-intercept, I want to divide everything by 7, okay? So then I'll have y equals negative 9 over 7x plus 74 over 7, which doesn't reduce. Or, if I want standard form, I'll just add the 9x over. 9x plus 7y equals 74. And again, it's just up to whatever the situation is, or if it don't tell you, like in this problem, right, I didn't specify, either one is correct. Okay, so now that you see that these two problems pretty much work the same, except just the differences in the definitions of those words and how I handle the slope at the beginning, pretty much those are the same problem other than that, right? There's another little side dive that you can do here. Anytime you have one of these parallel or perpendicular problems like this, and you're working from general form, okay? The slope in general form is based off of the numbers in front of x and y. And the other number is just kind of part of where it's positioned, the point, if you will. In any one of these situations, it's quick and easy for you to get to something parallel or perpendicular just by changing around a couple of the numbers without actually doing any major changes. So watch. Notice with parallel, do you see the 5x plus 2y? And here it is again, 5x plus 2y. That's not a coincidence. In lines that are parallel, if you're in standard form, you don't need to change the x and y's because that's just the slope, which, remember, with parallel lines is equal. So if it says, hey, here's a general equation of a line, make something parallel. The only thing you need to change is the number on the end. So then the question is, well, how do I know how to put something on the end? Well, this is what you know. You know 5x plus 2y equals something, right? I'll put capital C for the general form. And then I've got a point with an x and a y value, don't I? If I plug those in, I have 5 times 13 plus 2 times negative 2, right? That's 65 minus 4. 61 is C. And you'll notice that's exactly the equation that we have. So I would know, oh, it's parallel. I'm going to copy the 5x plus 2y, right? And that works in standard form. It also kind of works with slope-intercept, but it's much more straightforward in standard form. And then you can calculate the C just by plugging the point in and then using those numbers appropriately. The perpendicular one has a very similar process. You just have to remember that perpendicular slope you actually have to change a little bit, right? But notice with the line, do you see the 7x minus 9y? And then look at the answer, 9x plus 7y. Perpendicular slopes are opposite and reciprocal. Well, where's the opposite come in? This was a subtraction. Look, now it's an addition. And then the rise and the run, right? The 7 and the 9 just switch, 9 and 7. Again, not a coincidence. And yet, how do I calculate the 74? Once I look at this line and say, 7x minus 9y, I'm going to swap and change the sign. So I know that it's 9x plus 7y equals something, right? Again, I could just plug in my point, the 2 and the 8. 9 times 2 and 7 times 8 is 18 plus 56, which is 74, is equal to C, right? So which is what we got. Okay? So those are things that you don't necessarily have to remember. It's just in case you like having those other alternate methods and you practice them and things like that. Also, those two little ending are kind of gateways into some linear algebra things for some of the math people who want to go further. But if you don't like those little side shortcuts and you prefer to see the steps, which if you're practicing for the first time, I totally recommend that. Just sticking with the main process and just remember one process and just always practice that one process, right? Totally. Okay. So before, on the way out, just take a look at what these two situations look like in GeoGebra. I'll map them out for you. And I hope all of this has helped you understand linear equations in two variables. Let's look at all 4 of those problems that we just worked out. The first problem was one that started with the points 0, 3, and 3, -1. And we claimed that our equation was y equals -4/3 times x plus 3. Notice that's exactly what it is. It's the line that goes through those 2 points. It has this particular slope of down 4/3. Next we had the points -6, -1, and 8, 4. Okay. And then we claimed that it was the equation y equals 5/14 times x plus 8/7. Again, notice it's exactly what we were talking about. It's the line that goes through those 2 points. There's that equation. Then we had one where I was asked to make a line that goes through the point 13, 2, -2. That's right, 13, -2. Right here. So let's zoom out a bit just to be able to get that in there. And then it had to be parallel to the line 5x plus 2y equals 13. Okay? So it needs to be parallel to this line and go through this point. And one of the equation forms that we wrote was y equals -5/2x plus 61/2. And you can see the lines are parallel
They're going in the same direction. They're never going to touch. And it does indeed go through the point that we called for. The last one there asked us to create a line that went through the point 2, 8. Okay, so like this. And it needed to be perpendicular to 7x minus 9y equals 1. So there's that line. And my line needs to be perpendicular to him and go through this point right here. We claimed our equation was y equals negative 9 over 7x plus 74 over 7. And there you go. It goes through the point in question. It does look like it's perpendicular, but remember in math, you know, see things like this, you don't ever want to take it for granted. Let's compute the angle between these two. And you can see it is indeed 90 degrees. They are perpendicular and it does go through that point.